Assalamu alaikum guys. Today's topic is electronic spectra of molecules. In this topic, we know that how fluorescence and phosphorescence occur. The energies of rotation and vibration in a molecules are due to motion of its atomic nuclei, which contain virtually all the molecules' mass. The molecule's electrons also can be excited to higher energy levels than those corresponding to its ground state. However, the spacing of these levels is much greater than the spacing of the rotational or vibrational levels. Electronic transition involves radiation in the visible or ultraviolet parts of the spectrum. Each transition appears as a series of closely spaced lines called a band. Due to the presence of different rotational and vibrational states in each electronic state, all the molecules exhibit electronic spectra. Since a dipole moment change always accompanies a change in the electronic configuration of a molecules. Therefore, homonuclear molecules such as H2 and N2, which have the neither rotational nor vibrational spectra because they lack permanent dipole moment. Never, nevertheless, have electronic spectra whose rotational and vibrational fine structure enable moments of inertia and bond force consist to be found. Electronic excitation in a polyatomic molecules often lead to a change in the molecule shape, which can be determined from the rotational fine structure in its band spectrum. The origin of such change lies in different characters of the wave function of electron in different states, which lead to corresponding different bond geometries. For example, the molecules beryllium hydride BeH2 is the linear H bond Be H bond in one state and bent in another. Bond of H uh, trans convert into downward. Fluorescence. A molecules in an excited electronic state can lose energy and return to its ground state in various ways. The molecules may of course simple emit a photon of same frequency as that of photon it absorbed, thereby returning to the ground state in a single step. Another possibility is fluorescence. Here, the molecules give up some of its vibrational energy in collision with other molecules so that downward radiative transition originates from a lower vibrational level in the upper electronic state. Fluorescent radiation is therefore of lower frequency than that of absorbed radiation. Fluorescence excited by the ultraviolet light has many applications. For instance, to help the identify minerals and biochemical compounds, fabric brighteners that are sometimes added to detergents absorb ultraviolet radiation in daylight and then fluorescence blue light. Now, fluorescent lamp are mixture of mercury vapor and an inert gas such as organ inside a glass tube gives off ultraviolet radiation. When an electric current is passed through it, the inside of tube is coated with a fluorescent material called a phosphorus. Uh, Fluorescent material name is phosphorus inside the tube that emit visible light when excited by the ultraviolet radiation. When ultraviolet radiation excited, The phosphor emit visible light. The process is much more efficient than using a current to heat a filament to incandescence, as in ordinary light bulbs. Phosphorescence. In molecular spectra, radiative transition between electronic state of different total spin are prohibited. A situation in which the molecules in its singlet total spin quantum number is s is equal to 0 ground state observes a photon and is rise to a singlet excited state. In this situation, a singlet ground state observe photon and rise to singlet excited state. In collision, the molecules can undergo radiationless transition to a lower vibration level that may happen to have about the same energy as one of the level in a triplet s is equal to 1 excited state. There is then a certain probability of for a shift to the triplet state to occur. Further collision in the triplet state bring the molecules energy below that of crossover points, so that it is now trapped in the triple state and ultimate reaches the V is equal to 0 level. A radiative transition from a triplet to a singlet state is forbidden by our selection rules, which really means not that it is impossible but that it has only a small likelihood of occurring. Such transitions accordingly have long half lives and resulting phosphorescent radiation may be emitted minutes or even hours after initial observed.